Section. Introduction. We're going to talk about a concept called dataset distillation. This is a process where we take a large dataset and condense it into a smaller, more manageable subset. The goal is to keep the most important features and characteristics of the original dataset, so that a model can learn just as effectively from this smaller dataset as it would from the larger one. This is becoming increasingly important as the size of data and models continues to grow. Dataset distillation can help level the playing field, allowing researchers with limited resources to participate in cutting-edge model training and application development. It can also help address some data privacy concerns, as personal data might be excluded from the distilled dataset. However, many existing dataset distillation methods struggle to scale up to larger datasets. They work well with smaller datasets like CIFAR, Tiny ImageNet, and downsampled ImageNet 1K, but have difficulty with larger ones like the full ImageNet 1K. In our study, we're going even further and looking at the full ImageNet 21K dataset. This is a first-of-its-kind effort to handle such a large dataset for dataset distillation. We're using a simple but effective curriculum learning framework, and we've developed a robust strategy to train on the complete ImageNet 21K. Our approach starts by training a model to encapsulate knowledge from the original datasets. We then introduce a refined training recipe that improves the results on ImageNet 21K. During the data recovery, synthesis phase, we use a strategic learning scheme where parts of images are updated based on their difficulty. This is done by adjusting the lower and upper bounds of the random resized crop data augmentation throughout different training iterations. We're exploring three learning paradigms for data synthesis: standard curriculum learning, reverse curriculum learning, and constant learning. Curriculum learning is a method where a model is first introduced to simpler concepts and then gradually exposed to more complex ones. Reverse curriculum learning, on the other hand, starts with the most challenging tasks. We're also looking at how to change the difficulties of training samples. Random resized crop is a method that randomly crops the image to a certain area and then resizes it back to the original size. This ensures that the model is exposed to different regions and scales of the original image during training. Our proposed curriculum data augmentation, CDA, is a heuristic and intuitive approach to simulate a curriculum learning procedure. It's highly effective on large-scale datasets like ImageNet 1K and 21K, achieving state-of-the-art performance on dataset distillation. We're motivated by the fact that large models trained on large-scale datasets tend to outperform smaller models and those trained on limited data. These models are crucial in solving complex industrial problems and enhancing the development of AI-driven products and services. We've conducted extensive experiments on the CIFAR, Tiny ImageNet, ImageNet 1K, and ImageNet 21K datasets. Our proposed approach achieves an impressive accuracy of 63.2% on ImageNet 1K, surpassing all previous methods by substantial margins. When tested on ImageNet 21K, our method achieves a top 1 accuracy of 35.3%, which is closely competitive with the model pre-trained with full data, while using 50 times fewer training samples. Section Summary. Dataset distillation is a process of condensing a large dataset into a smaller, representative subset while preserving essential features. It is crucial in the era of large data and models, as it allows researchers with limited resources to participate in state-of-the-art model training. In this study, the authors propose a curriculum learning framework for dataset distillation on the ImageNet 21K dataset, achieving impressive accuracy and outperforming prior methods. Section. Approach. Our approach is centered around the concept of dataset distillation. The aim here is to create a condensed, synthetic dataset that retains a significant amount of the information found in the original, larger dataset. Imagine we have a large labeled dataset, which we'll call D_O, and it contains many pairs of data points and their corresponding labels. Our goal is to create a smaller, distilled dataset, which we'll call D_D. This new dataset will contain synthetic data points and their corresponding soft labels, and it will be much smaller than the original dataset, yet still hold on to the essential information from it. The main objective of dataset distillation is to create synthetic data that results in a minimal difference in performance on the original validation data, when models are trained on both the synthetic and original datasets. We aim to optimize the synthetic data, D_D, to achieve this. Most research in dataset distillation uses datasets up to the scale of ImageNet 1K as their benchmark. In this paper, we show how to construct a strong baseline on ImageNet 21K, which can also be applied to ImageNet 1K, by using insights from recent studies and conventional optimization techniques. Our proposed baseline has shown to achieve state-of-the-art performance. We believe this contributes significantly towards understanding the true impact of proposed methodologies and assessing the gap with full original data training. We use a decoupled training framework to save computation and memory consumption on large-scale ImageNet 21K. The steps include: 1. Building a strong compression model on ImageNet 21K. For the model pre-training, we use a large label smooth of 0.2 along with cutout and RAND augment. This recipe helps achieve around a 2% improvement over the default training on ImageNet 21K. 2. Curriculum training for better representation of synthetic data. We use a well-crafted curriculum data augmentation during the synthesis stage to enhance the representational capability of the synthetic data. This step is crucial as it enriches the generated images by embedding more knowledge from the original dataset, making them more informative. 3. Post-training on larger models with stronger training recipes. Previous studies have encountered difficulties, particularly a decline in accuracy when using larger scale models. However, the data we generated show improvement with the use of larger models combined with enhanced post-training methodologies. We've also observed that maintaining a smaller batch size is crucial for post-training on synthetic data to achieve good accuracy. This is due to the generalization gap, which suggests that when there is a deficiency in the total training samples, the model's capacity to generalize to new, unseen data is not robust. In our approach, the key to data synthesis revolves around using the gradient information from both the semantic class and the predictions of the pre-trained model, paired with BN distribution matching. We use a data transformation function to augment input samples to various levels of difficulties. By integrating curriculum learning within the data synthesis phase, this procedure can be defined as curriculum data synthesis. The key for our curriculum data synthesis becomes how to design the data transformation function across different training iterations. We discuss several strategies to construct this in the curriculum scheme, including constant learning, CTL, curriculum learning, CL, and data synthesis by recovering. After synthesizing the data, a soft label is generated for post-training. Our proposed curriculum data synthesis has several advantages. It stabilizes training, potentially achieves better generalization on diverse model architectures in post-training, and reduces the chance of overfitting. Section Summary. The goal of dataset distillation is to create a compact synthetic dataset that retains essential information from the original dataset. In this section, the authors propose a strong baseline for dataset distillation on large-scale datasets like ImageNet 21K, incorporating insights from recent studies and using curriculum data augmentation to enhance the representational capability of the synthetic data. They also highlight the advantages of curriculum data synthesis, including stabilized training, better generalization, and avoidance of overfitting. Section: Datasets and implementation details. We've tested our method on a variety of datasets, including small-scale ones like CIFAR100 and larger ones like Tiny ImageNet, ImageNet 1K, and ImageNet 21K. We trained our models from scratch on synthetic datasets and then checked their accuracy on real validation datasets. We used default values for the lower and upper bounds of crop scales, which were 0.08 and 1.0 respectively, and a decay value of 0.92. On the CIFAR100 dataset, our model outperformed all the baseline methods, including DC, DSA, DM, and MTT. We trained our model with an 800 epoch budget and found that our validation accuracy was better than all the baselines when using 10 and 50 images per class, IPC. We believe that our results could be even better with larger training budgets. We also tested our method on the Tiny ImageNet dataset. Our method outperformed the SRE²L method, with average improvements of 7.7% and 3.4% under 50 and 100 IPC settings across ResNet, 18, 50, 101 validation models, respectively. Our method was the first to reduce the top 1 accuracy performance gap to less than 10% between the distilled dataset using 100 IPC and the full Tiny ImageNet dataset. On the ImageNet 1K dataset, we used a ResNet-18 model and 1K recovery synthesis data. We found that results for very straightforward or challenging scenarios were below the baseline accuracy of 44.90%, especially when the difficulty level was either very high or very low. However, using a larger cropped range helped to avoid these extreme scenarios and improved performance. We also experimented with reverse curriculum learning, where we started with the default cropped range and gradually moved to optimize the whole image, shifting from challenging to simpler optimizations. However, this approach did not improve the quality of the generated dataset compared to the baseline. Our experiments with curriculum learning showed that our method improved the validation accuracy compared to the strong baseline, with average improvements of 6.1%, 4.3%, and 3.2% on RESNET 18, 50, 101 across varying IPC configurations. On the ImageNet 21K dataset, we pre-trained models and initialized them with ImageNet 1K weight. These models showed a 2.0% improvement in accuracy, while models initialized randomly achieved slightly better accuracy. We used these pre-trained models to recover ImageNet 21K data and to assign labels to the synthetic images generated. We performed validation experiments on the distilled ImageNet 21K using 10 and 20 IPC. This resulted in an extreme compression ratio of 150 times. When using 10 IPC, the models were trained using a distilled dataset that was only 1% of the full dataset. Despite this, the validation accuracy was over 20% and 30% on RESNET 18 and RESNET 50, 101, respectively. Compared to the baseline method on ImageNet 21K, our approach achieved an average improvement of 5.3% under 10/20ths IPC. This shows that our method can maintain the essence of the dataset despite high compression and can improve accuracy over existing methods. Section Summary. The effectiveness of our approach is verified on various datasets, including CIFAR 100, Tiny ImageNet, ImageNet 1K, and ImageNet 21K. We train models from scratch on synthetic distilled datasets and report the top 1 accuracy on real validation datasets. Our CDA method outperforms baseline methods on CIFAR 100 and Tiny ImageNet, and it also reduces the performance disparity between the distilled dataset and the full Tiny ImageNet. Additionally, our approach achieves commendable accuracy on ImageNet 21K, even with extreme compression ratios. Section. Ablation. In our study, we introduced 3 different types of curriculum schedulers, step, linear, and cosine, to manage the lower limits on data cropped augmentation. As shown in our figure, the process of distilling the dataset is split into 2 stages by a milestone. We found that both the linear and cosine schedulers, which gradually decrease over time, are robust across various milestone configurations. They also tend to improve accuracy performance when the milestone is reached later in the process. The cosine scheduler slightly outperforms the linear one in terms of accuracy towards the end. As a result, we decided to use the cosine scheduler, setting a milestone percentage of 1.0, to control the minimum crop ratio according to the principles of curriculum learning throughout the synthesis process. We also conducted a study to evaluate the impact of using smaller batch sizes on the general performance of models when the synthetic data is limited. Our results, based on the distilled ImageNet 21K from RESNET 18, show that as the batch size decreases, validation accuracy increases, peaking at 16. This suggests that smaller batch sizes improve performance on small-scale synthetic datasets. However, this also leads to more frequent data loading and lower GPU utilization in our case, extending training times. To balance training time with performance, we chose a batch size of 32 for our experiments. One of the challenges we faced was ensuring that distilled datasets effectively generalize across models that were not seen during the recovery phase. In previous approaches, synthetic images were optimized to overfit the recovery model. However, we found that our distilled datasets show less dependency on specific recovery models, thereby reducing the issues associated with overfitting optimization. We also studied the advantage of the curriculum on synthetic image characteristics. We found that our curriculum data augmentation, CDA, images closely resemble real ImageNet images in prediction accuracies, better than the previous method, SRE²L. This suggests that using curriculum data augmentation improves global image prediction and reduces bias and overfitting in post-training on simpler, cropped images of SRE²L. We also compared the synthetic images produced by our CDA and SRE²L at different recovery steps. The images produced by SRE²L showed a significant amount of noise, indicating a slow recovery progression in the early recovery stage. In contrast, our CDA images established the layout of the entire image and reduced noise rapidly. The final synthetic images contain more visual information directly related to the target class plant. This comparison highlights CDA's ability to synthesize images with enhanced visual coherence to the target class, offering a more efficient recovery process. We also found that there is no additional training cost incurred between our CDA and SRE²L when the recovery iterations are the same. Specifically, it takes about 55 hours on 4RTX 4090 GPS to generate distilled ImageNet 21K with 20 images per class, and the peak GPU memory utilization is 15 GB. Finally, we found that distilled datasets, which contain high semantic images, have a higher representation capacity compared to the original datasets. This can be used to combat catastrophic forgetting and continual learning. We validated the effectiveness of our CDA in various continual learning scenarios. Our CDA distilled dataset notably surpasses SRE²L, showing an average advantage of 3.8% and 4.5% on 5-step and 10-step class incremental learning assignments, respectively. This demonstrates the substantial benefits of using CDA, particularly in mitigating the complexities associated with continual learning. Section Summary. The authors present 3 types of curriculum schedulers: step, linear, and cosine, to manipulate data augmentation during dataset distillation. They find that the cosine scheduler outperforms the linear scheduler in terms of accuracy, and they choose to implement the cosine scheduler with a milestone percentage of 1.0. Additionally, they conduct an ablation study and find that smaller batch sizes enhance performance on small-scale synthetic datasets, but lead to longer training times, so they choose a batch size of 32 for their experiments. Section. Related work. We're going to delve into the related work in the field of dataset distillation. This is a process that aims to create a condensed, artificial dataset that still holds onto the vital information from the original, larger dataset. The benefits of this approach are that it's easier to manage, it cuts down on training time, and it strives to achieve results that are on par with using the full dataset. There are 4 main strategies that have been used in the past to achieve this. The first is meta-model matching. This method optimizes the transferability of the model on the distilled data. It uses a 2-step process, an outer loop for updating the synthetic data, and an inner loop for training the network. Some examples of this approach include DD, KIP, RFAD, FREPO, and LIN-BA. The second strategy is gradient matching. This method involves a 1-step process of matching the distance between models. Some examples of this approach include DC, DSA, DCC, and IDC. The third strategy is distribution matching. This method directly matches the distribution of the original and synthetic data using a single-level optimization. Some examples of this approach include DM, CAFE, HABA, and KFS. The fourth and final strategy is trajectory matching. This method matches the weight trajectories of models trained on the original and synthetic data in multiple steps. Some examples of this approach include MTT and Tesla. The concept of curriculum learning was also introduced. This idea suggests that training models with a curriculum can aid in better optimization and can lead to improved generalization. Following this, various strategies for defining and designing curricula have been explored. One such strategy is self-paced learning, where the model itself determines the pace of learning and the progression of difficulty.